Okay, that's the recording started. Just a reminder that all the lectures are on the YouTube channel. Remember, there's a tab for that in Teams. And there's also a link in the notes. I haven't updated, I need to put the 2020, oh no, there it's there. So there's the playlist for this year's lectures. If you subscribe to all the YouTube things, you'll get updates. Plus, you'll boost my self-esteem just that wee bit to know that somebody's subscribed to my channel. What is it? Smash that like button, smash that subscribe button, and come back again and again. All right. So, as you saw on the syllabus, we're up to this week, which means we are talking about virtual memory management. So we're moving on from, or adding to what we were talking about last week with memory management strategies that you all picked up first time round and didn't need to go back and check again because it wasn't that complicated, was it? That's impressive that you can just do one eyebrow corner. That's a skill. You could be James Bond in the future. I'm aware that memory management was tricky, so I hope you have gone to look at it because this, as I say, is an extension of what we were talking about last week. Because you remember last week we were talking about how we could take the idea that we bring stuff in from backing storage and figured out how we were going to organize it. And we went from pulling everything in and chucking it in the first hole that we found to dividing memory and processes up into pages and frames and swapping those in. Well, today we're going to kind of continue that thought in that we have now got the idea that we have now got in place a system where stuff is brought in as we need it, that we can bring in any parts of a process, that they can be anywhere in memory. So the logical next step is to think, well, if we can already do that, why are we limited to the amount of memory that we have? Can't we just pretend that we have unlimited memory? And if we have unlimited memory, we could load in unlimited processes and run unlimited programs. The only twist being that when we actually use them, when we actually bring them to the foreground and use them, they would have to be brought in from memory, from backing storage into memory. That's what we want to talk about today, the idea that we could have virtual memory. The idea that we could have as much space as we want and only bring in what we need as and when we use it. Because remember, we have to have stuff in memory to run. We can't run it from backing storage. It has to be in memory. But we don't always use the whole program. I've got PowerPoint running here. You're watching a PowerPoint right now. Think of how many options there are in PowerPoint. And if you don't remember how many options there are in PowerPoint, let me show you. Look at all these menus at the top with all these different functions in them. Look at all the things that you can do with PowerPoint. And of course, a lot of these functions here have sub-functions that once you go into them, you can do other things. If I go in here and click on this, oh, I can't do it because I'm running it. But we're not using PowerPoint to do any of those functions right now. What are we doing? You're doing a slideshow to appear on the screen. None of those functions, none of that code that they've gone to the trouble of writing is actually being used. So the question becomes, why would we have it in memory? Why would we have the code that does a spell check? Why would we have the code that allows you to use pens on a slide? Why would we have the code that runs the help? Why would we have any of that stuff when all we're doing is showing a screen? So maybe actually we can pretend to have the full program in this massive virtual memory, but in our real memory, we just have the wee bits that's running, the pages that are running. And when you think about it, that tends to be a lot of how you use programs. So here we are using the bit of PowerPoint that shows a slide. And I'll stay in that wee bit of code, going round that wee bit of code again and again. If you're in Word, you're mostly in the type stuff in bit of code. Type stuff in and update the screen. 95% of your time, that's what you're doing. So maybe just have the type stuff in and update the screen part of the code in there. And we can extend that out to all of the other systems that we have. So that we can say, right, let's have just the bit that we need and only partially load the program. It means we can have programs that are as big as we need them to be, because there's no limit if there's no limit to virtual memory. Now, I'm going to keep saying that. It's not true, of course. There's always going to be limits, because even virtual memory has to be stored somewhere. If you look on your Windows system, you get a hidden file with your virtual memory on it, and it's basically just a big file on the hard disk. So there is a limit. But let's pretend we've got as much space as we need. There's a question in the chat about adding in memory, and I'll talk about it when we get to it, because I'm going to talk about adding in memory later. So I'll talk about it in real terms, and then I'll talk about it in ReadyBoost terms. Okay, so if we're deciding that we only need to use the bits that we need, we can have more things running, more running at the same time, which means that we can increase the CPU utilization. We talked about that a few weeks ago in terms of one of the criteria that we might want to use as being a good system. And of course, we speed things up, because if we don't have to load in the whole 5 gigabytes of a program from hard disk, we just need to load in one page. That will speed things up getting started. So that's what we want to talk about today. We're going to call it virtual memory. The idea that we've got a logical memory space as distinct from the amount of physical memory that we actually have in the computer. And we're going to do all those things. We're going to allow only parts to come in. We're going to allow processes to share addresses, because we talked about that in terms of DLLs, in terms of shared code, a shared spell checker, whatever it happens to be. So if we're going to have virtual memory, we need to have a virtual address space. In other words, we need to think about how memory is in our virtual memory. And in essence, we're going to think about it in the same way as we would do physical memory. The virtual address space will start at 0 until the end, whatever that happens to be. Remember, we've already got our physical memory split up into frames. So what we are going to do is split up our virtual memory into frames as well. So we're going to need to have something else. We're going to need to have a map in there. And the map is simply, here's our virtual memory split up into pages, which of these pages is actually in real memory and which of these pages is in virtual memory, which is shown here as being on a hard disk. Whether it's hard disk, SSD, whatever, doesn't matter. Point is, it's not main memory. So we've got an extra memory map in here that's going between our virtual memory and our physical memory. Now, we've got a few things that we need to take care of when we're doing this. And I've said before about programs needing some local storage to run. And we've talked about stacks that go from the top down and heap going from the bottom up. And before I continue with that thought, I've got a question about virtual memory and swap space. So is virtual memory swap space, or is that a separate thing? The swap space is how you enable virtual memory. So when we were looking at this slide here, all of these things here are in our swap space. So when we load our program into virtual memory, some of it goes into real memory and some of it goes into virtual memory, which is sometimes known as a swap space. So it's an enabler. Okay, so if we're starting this local storage for all our programs, remember we've got code and we've got data, but we've got transient data. So if you're typing stuff into Word, that data is going to increase as you go along. So what we do is we start them at different ends to leave all the space in the middle to say, okay, we will, excuse me, start that at a particular page. Or to be precise, because it's in physical memory, a frame. And as it gets bigger, we'll take extra space for it as we need it. So as your Word document gets bigger, we'll take extra frames to store the data. We can also manage it so that we can have shared pages. So these shared libraries can also be in there somewhere. Okay, so these are the sorts of things that we want to have. So let's think about how we might go about making that happen. And the first way that we can do is something called demand paging. So let's think about what happens when we run a process. Traditionally, what we've said is the process is stored on a disk. It needs to run from memory. Let us go to the disk, load in the whole process into memory, and let's get started. And that's what you've got here. A program loads in here, another program here. So we're bringing in the whole process. But we don't use the whole process. Like I said, we don't use all those functions in PowerPoint. We don't use the spell check. Why are we bringing the spell check page into memory? Why do we need it there? And the answer, of course, is we don't. So why would we bring that in at the start? Let's instead think about bringing things in only as they're needed, only on demand when they're asked for. That brings in some problems of its own. So we'd load in the first part of the program, and then that first part of the program will start running, and it may reference other parts of the program. They may or may not be in memory. So if it's not in memory, we would need to go out and bring it in. We also need to remember that there might be an error happening because programs can make mistakes, and they can ask for bits of memory that they shouldn't even have access to. So we need the error part, but we also need the not in memory part. Doing it that way is called lazy swapping. We basically don't load anything until it absolutely positively is required. And we also need to put in some functionality there. The operating system needs to have something that says, okay, it's time to go and get a page and bring it in. And that is given the stunningly original name of a pager. So how does the pager work? Well, we need to think about what we're doing. We need to think about what pages we want. So we've got a list of pages that are in a process. Some of them are in memory. They're valid pages. Some of them aren't in memory. They are invalid. And remember, we saw that last week where we had the frame, where we had the page table with the frame number and whether it was valid or invalid. So we can continue that thought now with the pager. If they're in memory, we're fine. But if they're not memory resident, we need to figure that out. So we use our invalid bit to say, okay, invalid, not in memory, we need to go and do something here. Specifically, we need to go and get this page and bring it in. So here's an example. Here's the logical memory. Now, rather annoyingly, the logical memory in this example seems to be smaller than the physical memory. So what I'm saying at the moment is the logical memory is just a part of what it is. We haven't shown it all. Regardless of that, you can see that we have a page table that says frame 0, which is A, is in physical memory at location 4. There's A. Frame 2 is 6. 6 is G. G is at frame 2 is C. C is at 6. 5 is F, and that's at 9. So those three are valid. The other ones are invalid. Now, look at what we've got, and that's relevant to the question about the swap space. Because our process is completely in backing storage here. A, B, C, D, E, F, G, H. It's all in there, but parts of it are in physical memory. So we store it all in our swap space and bits of it in physical memory. The ones that are in physical memory are got the valid bit set. The ones that aren't are invalid. So if we try and load in B, B is invalid. It's still outside memory. The technical term for that is a page fault. Remember, it has to be in memory to run. If it's not in memory, that's a page fault. We need to bring it into memory so that we can run it. So we make sure that it's not an invalid reference, first of all. And if it's not, we just say, okay, it's not in memory. We need to do a few things. We need to find a frame that's free. In other words, what doesn't have anything in it? 1, 3, 4, 6, 7 here. And then we need to say, okay, we want B. We need to go and swap that in to memory and update our page frame to say, our page table to say that that frame is now valid. We've just gone and brought it in from disk. And that happens like this. So you've got your process running here. It asks for a piece of memory. That goes to the page table. The page table says, nope, that's invalid. I don't have that page in memory. That's trapped. That's the page fault. And the operating system says, okay, well, I know where that is. Let me go and ask the hard disk for that piece of memory, load it back into a free frame in physical memory, update our page table to say, yes, we now know where it is and it's valid. And we've got this one here that says restart instruction. So go back and redo the instruction. And the reason for that is we don't want to hang about. We don't want the CPU to be hanging about while it notices it doesn't have a bit of memory and the operating system takes over and goes to the hard disk and loads up a hard disk and brings that into memory and updates speed. The CPU's got better things to be doing. So in the same way as we go through our, remember our process stuff, where it went from ready to running to waiting, in essence, this process will go into the wait queue until it's loaded. And then once it's loaded, it can go back into the ready queue and restart again. So the process here is similar to when a process gets swapped out. We store its state, wait until it's all ready to go, because this is just another type of I/O. And then once it is, it goes back into the ready queue, ready to restart that instruction. Is that okay? Before we move on? Do a couple of nods, a couple of thumbs up. Okay. So let's think about how this is going to work in practice. So there's, you've got, as with all of these things, it's up to you how you implement this stuff. So at one end, you could say, nah, let's not bring in anything. We don't know what we're going to have. Let's not bring any pages. Instead, let's just start. Go to the first instruction, and if the first instruction isn't in there, then it will create a fault and it will go and bring the page in. And that will happen with every process when it's first accessed. That's called pure demand paging. Wait until it starts and then go get it. However, those of you who think back to your little man computer, it wasn't just about annoying you and doing assembler. It was to think about what's happening inside the computer. Now think about how some of you wrote it. Not everybody, but some of you. Some of you said, hang on a second, just to bring it up. So, some of you had code, and remember the code just shows us numbers in the mailboxes. But you also decided that you're going to store your inputs somewhere. This program does the same thing. It stores the input in memory location 99. So the instruction is up here. The data is here. That might be more than one page. So that instruction could actually need 2 pages. One for the data, one for the instruction. And if you extend that out, you can easily imagine how you might need more than one page. If you had a simple add with 2 values that were in different parts of memory, you might need 3 pages, one for the instruction and one for each piece of data. So you might actually have multiple pages that you require. So you might have multiple page faults. Now, we are lucky in that it doesn't happen a lot. There's a thing that we call locality of reference. And again, you'll have seen it when you did your Little Man Computer. Code tends to stay in its own wee loops in its own wee block. So it might move about for a while. So you maybe had a block that got all your inputs, and then a wee block that did all the sorting. But the code tended to stay within that. That's called locality of reference. So it's not quite as bad as that, but it can happen. So maybe what we need to do is add in some hardware support to speed all this up, because this is going to take time, and that's going to slow us down. And if those blocks are even more complicated, we might have issues. Because remember what we've got to do. In the worst case, we stop, save the process state, run an interrupt because it was a page fault, make sure that the page is actually legal, check whether it's on the disk, read it from the disk, so do the I/O. When the I/O is done, move it back into ready, and then run your process again by restoring the registers, getting the correct memory location, now it's in memory, and then resuming. So there's a lot of things that you have to do here. Some of them are fast. You know, they're fast. We've done them all the time. Saving the registers in the process state. Well, we do that all the time when we're moving around the processes. But going out to I/O and bringing in some memory, that's going to be slow. So the more page faults we have, the slower the system is going to be. And we can start to work that out. P here stands for the probability. If we don't have any page faults, then the effective access time is just the access time from memory. If we know that we're going to have a page fault, then every access time is the amount of time to access memory plus the time to go and get the page from disk, bring it in, and also quite possibly swapping a page out. There might be two I/Os here, because we've been looking at the case where you have a free frame. What if that's filled up? You might need to swap something out before you can swap something else in. So you might have two input outputs to do. So your access time is your memory access plus the page fault plus two swaps. And as I say, the stopping and starting, we do that all the time. It doesn't take a lot of time, but the reading of the page, saving the page, that takes lots and lots of time. And you guys have come across this before. You guys have come across this when you've run too many programs on your system. You go to move from one to the other, and this is what's happening. It realizes that your physical memory is full. You want something that's not in physical memory. It pauses, it takes something out of physical memory, loads what you need, runs that, and then your system goes, oh, but now I'm back to this other process, which you've just swapped out of physical memory. So it pauses, takes out a page, brings in another page, runs that, and all of a sudden, very quickly, your system just slows down and down and down and down until what it's doing is spending all its time swapping stuff in and out and very little time actually doing anything. There's actually a term for that. It's called thrashing, where you spend all your time swapping stuff in and out of memory rather than doing things. So we're never not going to have page faults, but we want to make them as few as possible, because we can very quickly slow down our system. You've got an example here if the access time is in nanoseconds and the page fault is in milliseconds, then working it all out, your system can slow down by a factor of 40. Weirdly, faster CPUs mean that the factor's gone up because hard disk speeds haven't increased that much, but your memory access time probably has. So the slowdown is actually more noticeable. So what we need to do is make sure that we have as few page faults as we possibly can. And we can turn this equation around to say, well, if we can work out how much the slowdown is, we can say if we want to have a slowdown of no more than, and here we say less than 10%, we can work that out that we only can afford to have one page fault in every 400,000 memory accesses. Okay. Don't worry if you don't follow the sums, just remember that there is an effective access time and it's about the probability of whether you have a page fault. So how do we make this faster? How do we optimize this? Well, maybe we can have a swap space, which goes back to Fraser's point. Instead of just having a straight file system, let's have some swap space. In other words, dedicated space that's for our swap file, for our virtual memory, rather than just a standard file system access. Because we've allocated it, because it's contiguous in memory, one huge chunk of memory, we can get faster access. We can also use this locality thing. So we've said that we stay round about the same place in a program. So quite often what happens is, if you want page 1, chances are you'll get on to page 2, and then page 3 and page 4, because you run through stuff. Maybe we could optimize it by not just getting page 1, but getting pages 2, 3, and 4, because we're going to a very slow device anyway. Let's have a whole chunk of memory and bring those in on the off chance, which means that when we get there, they're already there. We still need to write that. So when we start the process, it goes from the part of disk where the program stored. We need to save it into the swap space, but that's a one-off. We could, but we should, decide about this part as well. Because we're saying if we don't have any space, we need to swap stuff out. So we need to take the page, swap it back out to our swap space. So we need to free up some space, take that in, and take it back. What if we didn't have to? If we already have it on the disk, do we need to actually write it back out? And the answer is, as with most of these things, it depends. What does it depend on? Any thoughts what it might depend on? Oh God, he's asked us a question. Oh no. Alan, I can see you're unmuted, but you're not coming through.
I was going to say there, just as you said, oh no, he's asked a question. Is it to do with when you're using the program, like you were saying with PowerPoint, the part you're actually using? Like
Well, that's true for bringing in the missing page. But what about saving? So if we don't have any free frames, we need to swap out one of the frames that we have in memory back into swap space before we can bring in a new one. Do we always have to swap it back out? And if not, why not?
No, because you can just save it. You can save it directly to the hard drive outside of swap space.
No, that's not what I mean. And you wouldn't do that either, because the hard drive's slower, and that would just add in an extra layer of complication. Are there any times where you wouldn't need to save it back? Well, why would you need to save it back? You only need to save it if it's changed. If it's data, if it's something that you've updated. The code hasn't changed, so why would you bother saving it back when you've already put it all into our swap space in the first place? So maybe we don't need to swap it out. Maybe we only need to do it if it's modified, if it's changed. So we can keep a record of where pages have been changed. In the same way as have valid and invalid, we can say, have we changed anything? Have we written to this part of memory? And if we haven't written to it, we can say, oh, fine, we can just kill that without even thinking about it. Nothing's changed. What would be nice though is if we could keep some free frames. Now that's not always easy to do, particularly as the load goes up when you have more processes running. But it would be nice if we had a pool of fill on demand. If we had a pool of free frames so that we could bring in stuff. Maybe one of the things we should be doing is thinking about how we save the changes. So here we have a process with 3 pages in memory, and they're shared with another process. Maybe it's the spell check stuff. So the spell check code is here. Process 1 runs a spell check, so there's results, so there's some data needing to be stored, and they're stored here. Process 2 hasn't. So we can get even more complicated. Process 1 has got a copy of page C because it's updated it. Process 2 has got the original page C because it hasn't changed anything yet. So we're using the same spell check code, but one of them has changed. So it starts, there's an awful lot of work that the operating system has to do to keep track of these things, figure out what's changed, what hasn't, what needs to be updated and what doesn't. Everyone happy with that before we move on? Yep, okay. Okay, we are roughly halfway through the slides that I have. So I think that's, and you've all concentrated for about 50 minutes. So I think that's probably a good time to have a break. Yeah, okay. We shall have a break then, and I will see you back here in 10 minutes.
Okay.
Okay, and we're back. Has anybody got any questions that's occurred to them while we were taking our break? Kelly has to leave early to. Apparently their son's going to dress up as a horrible lecturer for his Halloween party. I assume that's going to be the costume. Okay, I'm not seeing any questions. So we left it that we were talking about moving stuff in and out of memory to get a free frame. But what if we don't have any free frames? What if memory's all been used up by all the processes? And of course, there's a question there already. If memory's been used up, how did we decide to use up that memory? Did we split it up between the processes? Did we give it on demand? What was the choice? I'm laughing. If you're not watching the chat, that's why I'm laughing. It's actually quite impressive, I have to say. There's a dinosaur doing a front flip into a boat, and it's quite impressive. And of course, I'm now seeing that the costume isn't a stressed out lecturer. Instead, it's a dinosaur inspired by the operating system book. Well, excellent. That's what I like to see. Engagement with the module. Okay, so how did we decide who was getting all this space and memory? And more to the point, now that we've filled up the space, who loses? How do we decide which pages come out? We could find something that's not in use, but how do we know it's not in use? How do we make that determination? Do we just swap it out? Do we replace do we terminate the process? What's our reasoning? And of course, what algorithm do we use to allow us to do that? First thing we want to do is the one that I pointed out earlier. So we want to minimize our I/O. So we will introduce an extra bit. We've already got in memory and not valid or invalid. So let's add in an extra wee note to say, has this piece of memory changed? We call it, is the memory dirty? And if the memory is dirty, then we need to save it, because we need to save that change. And we need to do that for swapping out of memory. So that might be one of the things that we use. Maybe dirty pages are things that we shouldn't be swapping out as much if we can arrange it that way. Regardless, we're going to have the situation where we've got multiple users looking at the same looking at different logical memory as far as they're concerned. So their process is just running its own logical memory space. But that has to fit into physical memory. And here we've got two processes that take 4 pages. Our physical memory is 8 pages, but we can't use it all because the operating system has to go somewhere. That's what this monitor thing means. So we can't fit everything in. There's going to be a fight. Currently, B and M aren't in physical memory. They're in the swap space. But the program counter for this process is in here. So we need to load in. Problem is, where's it going to go? This process has got 3. This process has got 3. Who loses? Well, before we do that, let's figure out how we're going to do it. We need to get it from disk. So we know that we want page M. We know that's there on disk in the swap space. If we have free space, that's easy. Chuck it into the free space. If not, we need to select a victim from all the places here. Now, if we're going to have a victim, if we're going to swap something out, we also need to check whether that piece of memory is dirty. In other words, has it changed? If so, we need to swap it back out. And then we need to bring the one that we want, in this case M, into memory somewhere. So here, we're going to have it loaded in this page. And then we restart. But of course, because memory was full, we've got 2 page transfers. Writing out and bringing back in. So that will increase the effective access time. Okay. So we need to swap out the victim page and bring back in the new page. 2 IOs. And that's not good. So let's think about how we might approach our replacement. And before we do that, remember the difference between a page and a frame. One's for physical memory, one's for the process. One of the things we have to think about is how many frames to give a particular process. Do we split it up? Do we decide everything gets the same? Do we give some things more space than others? What's the algorithm that we're going to do? And then we need to decide on a page replacement algorithm, which ones are we going to swap out when we need to move things around. So what we're going to do is think about some different algorithms that we might use. In fact, algorithms that have been used in operating systems, maybe not now, but certainly in the past. So let's figure out what would happen using these algorithms. Now, all we're going to do is have a string. And this string here is just a list of numbers. These are the pages that we want. We want page 7 followed by 0, followed by 1, followed by 2, and so on. And we can do a couple of things. We can model that based on the number of frames that we have. In other words, how much space we have in real memory. And then once we've done that, we can figure out how many page faults it's going to generate. In other words, how many times do we have to swap it? So if we only had 1 frame, we load in page 7, then we want page 0, so we have to swap out page 7 and load in page 0, because we've only got 1 frame. And then we have to swap out 0 and load in 1, then we have to swap out 1 and load in 2, and so on. So the number of page faults is the number of times this number changes. And we can start to model that based on the number of frames that we have. And we can see what happens with the number of page faults versus the number of frames that we have. Now, just as an aside, one of the things you're always told is if you want to speed up your computer, add more real memory. In essence, this is why. The more real memory you have, the larger the number of frames that you have, the fewer page faults you'll generate because you can get more things into memory at once. And if you have fewer page faults, you'll speed things up because you reduce the I/O required. So in general terms, that's why the best thing you can do to a computer is add in more memory. Okay, so let's think of some algorithms. And actually, the algorithms are probably going to be familiar to you from when we looked at processes. First one we're going to look at is first in, first out. So here's our list of pages. We will assume that we have 3 frames and we can start working our way through it. So we need 7. That's loaded in. Not a problem because we've got 3 free spaces and just go in. Then we need 0, then we need 1, and they're just loaded in. However, we then need 2. So our algorithm is first in, first out. First one in was 7, so we swap out 7 and put in 2. Next one we need a 0. Well, we don't have to do anything here because 0 already exists. Next one is 3. Well, the last one that we put in was 0, so 0 gets loaded out and 3 gets put in, which is a bit of a shame because the next one we need is 0. So we've just swapped it out and we immediately have to swap it back into this space here. And you can go through that whole string, seeing where the pages have been loaded in. And we can then count out that there have been 15 page faults. And of course, it depends which pages we have, and you can work that through. And one of the things that you can do is try this string later on your own. There's also some weird stuff that can happen with this algorithm. It turns out that adding more memory, more frames, can actually cause more page faults depending on which pages you ask for. That's called Boulard's anomaly. And you can see it here. There's a point where we go from 3 to 4 frames where we actually increase the page faults before they come down again. So that's a fairly straightforward one, which means it's easy to implement. So basic operating systems do use this. But we would like to be a wee bit smarter about it. We might want to optimize it. Maybe we could decide to swap out the one that won't be used for the longest time. Except we're back into the same problem that we had when we suggested that we optimize our process replacement algorithm. How can we know what pages we're going to need in the future? On the other hand, as we did with processes, it gives us a yardstick. If this is the optimal algorithm, then we can work out how many page faults that we get, and we can test them against our other algorithms to see how well they perform against this optimal one. So our next approach isn't about what came in first, it's about what was used last. Which is the least recently used page? Which one didn't we bother having? So it's in memory, but we've not been to it in the longest time. So same string, same first 3, same first 4 actually, because our least recently used is the one that's been in there for longest. It's 7. Because we use 7, then we use 0, then we use 1. So we swap out the least recently used, which is 7, and that goes to 2. Next one is 0. 0 is still there. Next one is 3. Now, before we swapped out the 0 because it was just a strict first in, first out. But here we say, no, actually, we used 0. So let's not swap out 0. The least recently used of the ones we have in memory, 2, 0, 1, we work our way back and go 0 to, okay, there's the least recently used is 1. So that's what we'll swap out for 3. Next one is 0, same thing, it's there, don't need to do anything. Next one is 4, and again we work our way back. We've got 2, 0, and 3. Well, we've used 0, we've used 3, so our least recently used is 2. So we swap out 2 for 4. And you can work your way through to the end of that string. Works out that for this particular string and this number of frames, we get 12 faults. So better than first in, first out, but not as good as our optimal one, which had 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's pretty much in the middle. First in, first out had 15, I think. Optimal has 9. This hits in the middle with 12. How do we implement it? We just keep a note. We've got a clock in the computer. We take a note of the last time we used it. Smallest value is the least recently used. It's a wee bit slow though, because we've got a list of frames and we need to go through, was this the slowest, was this the slowest, was this, and it takes a while to go through things. So we could maybe optimize that. Those of you that know about programming will know about a stack. So we could have a stack of page numbers in a double linked list. And the programmers are going, and the non-programmers are going. Again, it doesn't matter. We can organize it so that we can optimize it simply so that every time we add one in, we can change the list. And it simply puts the least recently used at the front. The other nice thing is about least recently used is that as we add more frames, we do get a better performance. We don't have that anomaly. So here's a stack in the frame. So it simply puts in the least recently used in order. And again, if you don't know about stacks, don't worry about it. It's just remember it's a way of optimizing it. As I've mentioned earlier, if we have to do this a lot, we can start thrashing the system. And that's where we get to the point that there's no free frames. We need pages, we load them in, but before we do that, we have to unload it. And then we find that we need it again. It's this thing here, we unload it simply to find that we have to load it in again. So we can get to this point where we're spending more time getting page faults and having to swap things than we are actually doing any work. In a graph form, it looks like this. We're doing lots and lots of work, until all of a sudden we're spending so much time swapping that we do nothing other than swap. Now, as we said, this works because code tends to stay in the one place. We will do the bit where we edit, then we'll do the bit where we bold, then we'll do the bit where we edit again, then we'll do the spell check. So things move about, but they stay in specific chunks, which is what that means. When it says the process migrates from one locality to another, it means that in the code, we're doing this bit, and then we'll do that bit, and then we'll do that bit. But within that, it stays in the same small bit. And that can be an issue where we're doing either lots of processes or processes that move within their own code quickly. So it might go to one bit, come back, go to another bit, come back. Say you're, I don't know, say you're rendering an image. You take that bit, and then you go to the render, which goes to the color check, which goes to the shadowing, and then you go back and do the next one, and then works its way through the program, jumping about all over the place. That can cause thrashing as well. And what we really want to have is the locality, the part in the program that you're going within to be less than the memory size that you give it. That way you don't have to swap things out. So the sum size of the locality should be less than the total memory size. But greater than the total memory size, we get thrashing because it has to go in and out. There's a diagram of locality, and you can see what's happening here. This is an execution time, and you can start seeing that things stay in the same place in terms of memory addresses. They tend to be in the same place. And then when they swap, they'll swap from one to the other. So here we were doing it in here, and then it swaps here, but we've stopped doing it here. Okay, so things tend to stay in the same place. What that gives us is the idea that, well, the bits that we need to run, that's our working set. That's a bit of that's a set of memories that we are actually using and we will need. Maybe we can start to work out what that working set is using all the processes that we have. Look at the number of pages that we've referenced in those processes and try and ensure that we keep all those processes within our real working memory. If we can, we're fine. Everything comes in, everything stays in memory, and we just do what we do. We work our way through memory. But as soon as we have too many processes, or a process that is jumping about within its own working memory, the working set of pages becomes larger than the memory that we have, and we start to get thrashing. Okay, but in simple terms, that's when we have just too much going on. If we keep track of the working set, though, what we can say is, okay, well, we're having a problem here. Things are just slowing down. Every time we try and do anything, we're swapping stuff in and out. Maybe what we can do is pause something, allow one of the processes to finish whatever it's doing, and then we can bring the other process back in and let it do that. So we can say if the number of frames that we need is larger than the amount of memory, suspend a process. Just say, nah, we're not doing that just now. And you can do that in one of the ways that we've looked at before. The one that's got the least to go, the one that's got the highest priority, you know, whatever it happens to be. So we just suspend one so we can stop the thrashing until we can free up some more memory, hopefully by one of the other processes finishing off. But of course, we need to keep track of that working set by saving it somewhere so that we can know which ones we are using. That starts to get a wee bit complicated. So maybe we can just say, well, forget that. Rather than keeping track, let's just say if the number of page faults is bigger than n, let's pause stuff. In other words, we can set an acceptable page fault frequency. And if it's too much, we just don't take on any more work. We stop processes being created, or we pause others, or do both. And what we tend to find when we analyze these things is that there's a direct relationship here. There's a direct relationship between the working set and the page faults. Not surprisingly. As we're doing more work, as we're loading in more, the page faults go up, and then the processes might finish, and the page faults go down again, and they trundle along. We're starting to do more work, more page faults, until whatever we were doing finishes and it trundles down again. And that's exactly what you've seen when you've been working on your own machines. You start up stuff, it can slow down. So you think, oh no, stuff this for a game of soldiers, and you kill a program. Just, you know, let's stop that one just now until your system settles down again. Some operating systems decide, well, I don't need you to kill it, I'm just going to pause it and I'm not going to do anything with it. That becomes easier depending on the type of system it is. You tend to work on systems that are very much user-focused. In other words, it's just you and your computer, so it wants to give you a good response. Other systems might be focused on working on batch jobs or doing a workload. So it's easy to say, oh no, this was just too far, let's pause this one until we're done. As an example, here's what Windows does. It uses demand paging with clustering, by which I mean that thing that I was saying right at the start. If we want page 1, well, maybe we bring in pages 2, 3, and 4 as well, because the chances are we'll need them because of this locality thing. You have a minimum and maximum for the working set that you can have. So we guarantee a process that you can have a minimum set of pages up to a certain maximum. After that, you don't get any more. And as memory, the free memory falls, that amount that you're allowed gets trimmed, gets smaller and smaller and smaller, so that you can get some free memory. And that is virtual memory management. Questions? Alan's happy it's over. Nope, I'm not seeing any questions. Okay, I'm not seeing any questions, so let me stop the recording